Hello everyone. Today, the LD lesson, we're talking about lesson 2.5, which is postulates and paragraph proofs. So our objectives will be identify and use basic postulates about points, lines, and planes. Our secondary objective will be to be able to write paragraph proofs. Okay, and so let's define our first definition here. A postulate or axiom is another word for it. We'll use postulate in this class a lot. Okay, a postulate is a statement that is accepted as true without proof. Okay, so it's things that are accepted as true that we do not have to prove. So in this lesson, we're going to talk a lot about postulates that have to do with points, lines, and planes. Points, lines, and planes. So these things are accepted that are true about points, lines, and planes. So postulate 2.1, through any 2 points, there is exactly one line. So if I have 2 points, okay, there is only one line that goes through those 2 points. Okay, and in this case, it's a line N that goes through PR. There's no other line that can go through those 2 points. All right, through any 3 non-collinear points, okay, so 3 points that aren't all on the same line, so any 3 non-collinear points, there is exactly one plane, okay, and so in this case, plane K is the only plane that contains all 3 of those non-collinear points. Theorem 2.3 has to do with a line. Okay, a line contains at least 2 points. So if you've got a line, it's defined by at least 2 points. So any 2 points, P, Q, or R. Okay. 2.4, a plane contains at least 3 non-collinear points. So you guys can kind of see the connection here. So at least 3, so E, B, and C would be acceptable, right? Or LBC or LEC. Okay. You guys can kind of see the connections here. 2, 1, and 2, 3, similar. All right, and then 2, 2, and 2, 4. And we shouldn't say similar. These are actually the converse of each other. Okay, both cases here. 2, 2, the converse of 2, 2 is 2, 4. Okay, just flipped around there. So both those, all 4 of those, kind of all related there. All right, 2.5. If 2 points lie in a plane, then the entire line containing those points lies in that plane. So if there's 2 points on plane K, then that line M, that connects those 2 points, well, line M is also in the same plane, plane K. Okay, so that's 2.5. 2.6. If 2 lines intersect, then their intersection is exactly 1 point. So if lines intersect, there is only 1 point that's in common with them. There's only 1 point of intersection. And here, when 2 planes intersect, their intersection is a line. So if planes are just 2 planes are intersecting, their intersection would be considered a line. Okay, so that's our 7 postulates we're going to work with in this lesson. Okay. And so example 1, identifying postulates. All right, we're going to look at this. We're going to use this picture here, and we're going to explain how the figure illustrates that each statement is true, then state the postulate that can be used to show each statement is true. So here on this first one, let's call it A, planes P and Q intersect in line R. So plane P appears to be, and I'm going to erase a lot on this. This is plane P, and then Q. Q, I'll use another color for. Let's use blue. These 2 planes intersect in line R. So where do they meet each other? They meet each other at that line, which was labeled R. So the picture confirms that. What postulate has to do with planes intersecting? Okay, I believe that was that one we just finished up with. Okay, postulate 2.7. Okay, so 2.7, and what's it state? If 2 planes intersect, their intersection is a line. Let me abbreviate that. That's going to be way too much. Let me use some abbreviation there. I'm going to run out of room. I already ran out of room. So let's just say two planes intersect in a line. Two planes intersect in a line. Well, that's a summary of it. Okay. Let's do this. Let's call this example B here. Example B, line N contains points C, D, and E. So, well, what should we do? We should look for line N on this picture. So line N is here. It contains points D, C, E. Well, yeah, that's true. So the picture confirms that. Okay. What postulate? So we should be looking for a postulate about line containing points. I believe if we go back, and guys, this should be on your other side of the paper there. Line containing points looks like 2, 3. Line N contains points P, Q, and R. A line contains at least 2 points. So yeah, 2.3 would be the postulate that kind of confirms this one. So 2.3, a line contains, say, at least 2 points. This one contains 3. So, all right, let's look at example C here. Line N lies in plane Q. So, well, actually, I could have left that highlighted. We're still talking about line N, and that lies on plane Q. So, plane Q, use green here. Plane Q is this plane. Yeah, line N does lie on that plane. Okay, you got to remember that plane's going to extend infinitely this direction. It's going to extend infinitely this direction. Okay, in all directions the plane extends. Even out here, these pieces. Okay, is the plane. So certainly line N, the picture can confirm that line N is lying on plane Q. And now we just need to recall which postulate has to do with a line in a plane. So we go back, look at here, I think it's 2.5, yep, 2.5. If 2 points lie in a plane, then their entire line containing those points lies in that plane. So that's 2.5. Again, it references the points on the plane, which we have. Okay, we have the points, you know, on that line. They lie on plane N, or on plane, plane Q. Okay, and so that certainly that line does. So this is theorem 2. Or postulate 2.5. And it just states if 2 points lie on a line, lie on a plane, so does their line. So does the line, we'll say. And that the line connecting the 2 points. Okay, so just running out of space there, so just abbreviate. Let's make this next one, let's talk this D, example D here. Plane P contains points A, F, D. So plane P, again, that's my plane over here on the side. This is P. A, F, D. Absolutely, those are 3 non-collinear points. So if you guys remember, and you guys can flip back, I'm going to stop going back and forth here. Theorem, postulate 2.4. Okay, a plane contains at least 3 non-collinear points. Okay, and let's make this E and F, and I'll leave these to you guys. You guys pause and give them a shot there. Alright, so E says line R is the only line through points A and D. So we find A and D. Well, yeah, there's line R. Okay, so theorem or postulate 2.1 would confirm that. Okay, through any 2 points there is only one line. And F, the postulate there, postulate 2.6, lines R and N intersect at a point. So that one was again at the top of this page. So R and N intersect at, yep, a singular point, point D. So postulate 2.6 there, and you guys can abbreviate those. So that's a little bit of work in introduction to postulates. Okay, here we're going to determine whether each statement is always, sometimes, or never true, and we'll provide an explanation. So if two coplanar lines that intersect, so well, let's draw this part here, two coplanar lines. So we have a plane, and then we have two lines on the plane that are intersecting. So two coplanar lines intersect. Then the point of intersection lies in the same plane. So the point here lies on the same plane. Well, based off of our picture, yeah, that makes sense, okay? Well, why? So this is actually going to be always true, not just the way we drew our picture, but this is always true. So an explanation here. Okay, so I would go back, if I look at my postulates again, postulate 2.6, if two lines intersect, then their intersection is exactly 1 point. So there's only 1 point of intersection, okay? And then if we go back even postulate 2.5, so the support here would be, we said postulate 2.6. I'd also say postulate 2.5 helps here. If 2 points lie in a plane, then the entire line containing those points lies in a plane. So if this point is on the plane, then this entire line is on the plane, and this entire line here is going to end up being on that plane. So I would think those are the two postulates that kind of support this idea. Alright, so B, 4 points are non-collinear. So given 4 points, is this always, sometimes, or never true that they're non-collinear? Okay, well, it's certainly not always true because, well, right here we have an example where these points are non-collinear, but there's also 4 points that are collinear. So it's not always, okay? It's going to be sometimes. Okay, you have the case here where A, B, C, and D are, all 4 of these points, collinear. They're all on the same line. Okay, but you also have the case of A, B, C, and E are not collinear. So this is a sometimes, okay? So it's just dependent on what points you're looking at. Okay? Alright, so let's get into a little more in depth here into actually proving some things. So to prove a conjecture, this is a conclusion. Remember, conjecture, conclusion, synonyms there. So to prove a conclusion, you use deductive reasoning to move from a hypothesis to the conclusion of the conjecture. So this is done by writing a proof. So we can use deductive reasoning, use our rules, our postulates, okay, to move from a hypothesis to a conclusion, which is a logical argument in which each statement you make is supported. Each statement you make is supported by a statement that is accepted as true. A proven statement or conjecture is called a theorem. Okay. So here's kind of the proof process. So step 1, list the given information and, if possible, draw a diagram to illustrate this information. So your first step, list what you're given and draw if you can, okay? Step 2, state the theorem or conjecture to be proven. So, hey, what are you trying to prove? Step 2. Okay, then create a deductive argument, okay? Forming a logical chain of statements linking given to what you're trying to prove. Justify each statement with a reason. Reasons include definitions, properties, postulates, and theorems. That's the deductive part of this. There's support, there's reasoning, and those reasons are definitions, properties, and postulates and theorems. And then the last step is just to state, hey, we've state your conclusion, state what you've proven. Okay, so let's practice this here. So write a paragraph proof. Okay, here we're going to kind of fill in the blank. So given that m is the midpoint of xy, write a paragraph proof to show that xm, segment xm, is congruent to segment my. So given, what's the given information? M is the midpoint of xy. That's what we were given. Okay, what am I trying to prove? Okay, and they've even provided a diagram here. The diagram here, xy, this is m is the midpoint. So to kind of correctly fill this in with the given information, what's it mean to be the midpoint? Well, that means these segments would be congruent, okay? So let's prove here. What are we trying to prove? We're trying to prove that xm is congruent to my. And I kind of spilled the beans there a little bit. But let's talk about it. So what we're trying to prove is what I've listed here on the diagram. We're trying to prove that xm is congruent to my. And why would that be? Okay. So steps 3 and 4 are kind of a combination. We make an argument and then we support it with a reason here. Okay. So if m is the midpoint of xy, then from the definition of midpoint, I said this earlier, kind of let it slip earlier, midpoint of a segment, what's the definition of a midpoint of a segment? Okay, well, it means that xm equals my. Okay, this means that xm and my have the same measure. Let's just say, okay, remember, equality is same measure, so not necessarily that they're congruent. It means they have the same measure by the definition of congruence. So again, we're stating, hey, definition. These things are my reasons. Okay, by the definition of congruence, if they have the same measure, if they're equal, the definition of congruence, if these segments are equal, then they're congruent. That is what we were trying to show, that they were congruent. So thus, they're congruent. We just restate what we've proven. Okay? And so, well, what did we just prove? We just proved the midpoint theorem. We started by saying m is the midpoint, show that those segments are congruent. We used a logical argument, we used deductive reasoning to do that, and we've done that. So now we call this, okay, once a conjecture has been proven true, it can be stated as a theorem and used in other proofs. So now we can use this in other proofs because it's now a theorem, and it's called, we call this one the midpoint theorem, theorem 2.1. If m is the midpoint of AB, then AM is congruent to MB. All right, so here we've got an additional proof. Okay, in the figure at the right, AE is congruent to DB. C is the midpoint of AE. So again, by the midpoint theorem, that means that these segments are congruent. The midpoint theorem we just proved. Write a paragraph proof to show that AC is equal to CB. Okay, so let's go through the steps here. I'll take you through the entire process of writing a paragraph proof. Even though more often we'll do a fill in the blank type, let's just go through the entire process here. So given, we were given that these segments are congruent, AE and DB are congruent. C is the midpoint. We were also given that C is midpoint of AE and DB. I'm going to have to extend here. So that's what we were given. Okay. We've got a diagram. Those are also congruent from the given because of the midpoint theorem. All right, what we're trying to prove, so we restate what we're trying to prove. That's this kind of the second step here. So prove that AC equals CB. So let's write a paragraph, okay? If C is the midpoint, which it was, that's given to us, is the midpoint, I said, of A, E, and D, B, okay? Then AC equals CE, and DC equals CB. Again, I've drawn that on the diagram. I just need to state it as part of my proof. Okay? And this is, well, what's the reasoning for this? Well, this is by the definition of midpoint. So that's my reasoning. Again, I state something and then I give a reason. Okay. So it's also true that AC is equal to 1/2 of AE. And BC equals 1/2 of BD. Okay, this is an important step. Okay, that's by the definition of congruence. Well, let's take it a little further here. If AE is congruent to BD, okay, then AE equals BD. This is by definition of congruence. Okay. So then AC, if I do a little substitution here, AC is equal to, I said it was equal to 1/2 of AE. Well, let's substitute AE out for BD or DB. Substitution there, okay? Because they're equal in that last step. So AC equals 1/2 of DB. That's just by substitution. You guys have done substitution before. Okay? Just changing out things that are equal. AE and BD are equal. So I'm changing out things that are equal. That's substitution. Alright? So AC equals 1/2 DB, which was also equal to CB up here. Okay, and so then AC equals CB. We can take out the middleman there. We can take out 1/2 of DB. Okay, so this part, cancel it out and say AC equals CB, which is what we were trying to prove. So we're done. At the end of a proof, draw a box, fill it in. All right. Your homework was up here. I kind of skipped over that. It's there. It's the next page on the module. I'll also have passed this out as long as we're here in school Friday. I'm planning on passing that out after our quiz. So thanks for watching. Everybody have a wonderful weekend.